Okay, thank you all for coming. I'm going to kick off for some of you will be the MSc in Reliable Embedded Systems, and for others will just be a short course. Are you going to be comfortable that close to the screen? Okay. Excuse me. How many of you have actually built embedded systems before? Through courses? In previous courses, nothing real. Okay? What about C programming experience? How much C programming experience have you had? Okay, much the same. C programs 5 pages long or more? Yeah. No hands going up? We don't do lectures. These are going to be seminars. By the time we've warmed up, it'll be more interactive. Okay. What we're going to cover from scratch, assuming you know how to program in C, we're going to spend this week looking at how you can use the C programming language to create embedded systems which have predictable behavior and can therefore be used as the basis of reliable applications. So this is one definition of what an embedded system is. It's anything that contains some kind of embedded processor, a processor hidden inside it. It's essentially a computer system. But as far as most users are concerned, it doesn't look like a standard computer. It doesn't look like a desktop PC. It doesn't look like a laptop PC, etc. You can argue by now as to whether something like a modern mobile phone is an embedded system or not, or is that now pretty close to a standard computing system. The divisions get a bit blurred. We're going to be looking at how you can create reliable embedded systems. Now, these processors form a core component of a huge range of systems. It's estimated that in this part of the world, you come across around about 300 of these devices every day of your life. Within the next 5 years or so, it's estimated that figure will go up to 1,000 or more embedded processors that you will encounter every day of your life. And you won't, as a general rule, even be aware that they are in the devices that you're using. So they're used in standard off-the-shelf products. Our main focus will be on embedded systems which are used in applications where high reliability, high integrity is a key design requirement. Satellite systems, medical systems, aircraft systems, automotive systems, defense systems. Systems where if the embedded application, the embedded system, the embedded code is not produced in an appropriate manner, this can have serious implications for the general public or people who are directly exposed to the systems that you're creating. We're going to focus on what are sometimes called deeply embedded systems, where the processor is completely hidden inside the application. It doesn't look at all like a computer system to most users. There's no conventional interface as far as most people are concerned. For these kind of applications, wide range of potential application areas. As will become clear later in the week, the techniques we're looking at are generally less useful for applications in which users add or remove programs. It's not impossible to apply the techniques we're looking at in those types of applications, but we're looking at applications which are generally one piece of hardware running one set of software. If the set of software is changed, that'll be carried out by a technician or an engineer or somebody who's qualified to upgrade that system. So it doesn't mean that the the adaptive braking system in your car wouldn't be updated. It just means that it's unlikely that you'd give the user access to do that. It would be carried out by somebody who understood the implications of what they were doing. It also means that the techniques we're focusing on this week are less suitable for applications such as a mobile phone in which the user may expect to have a suite of applications running and then gradually add new applications themselves to that system. The reasons for that will become clearer as we go through the rest of the week. So it focuses on reliability. For some systems, the reason why you need the system to be reliable is obvious. Medical systems, industrial systems, aircraft systems, etc. If it goes wrong, people will die. The other end of the spectrum, in general consumer products, the main reason for seeking reliability from a business point of view is to reduce warranty costs and also to reduce the development times. If you can build your system with predictable patterns of behavior, then it typically will have an impact on the time it takes you to test the systems you're producing. And those of you that are going on to do the full MSc program, by the time we get to the second module in this program, we'll be looking at ways of looking at test coverage. How can you ensure that for the system you've done enough testing? Sometimes there's a view that you can't do enough testing. You just keep testing and testing and testing for as long as you have. That, in an industrial setting, isn't practical. So we'll look in the second module at how you can determine the number of tests that are required in the application and how you can determine whether you've done sufficient testing. And you can only do that if the platform you're working with has predictable behavior from the start. Lots more about that to come. We run the whole program with a very simple structure. We run a number of seminars in each module. Generally, we spend the morning in seminars. I'll talk for about an hour or so. We'll have a brief break. I'll talk for up to about another hour. And then we'll give you some exercises to work on for the rest of the day. If you're studying for an MSc, the exercises that we give you to work on during the afternoon make up 40% of the marks for that module. Up to 40 credits out of 100 credits for this module will come from the exercises you do during the afternoon sessions this week. The remaining 60 credits come from the exam. And if you're doing the MSc, then the exam will take place at the beginning of the next module that you sit, and we can talk about the dates of that with you individually. So there's a written exam, closed book examination, runs for 2 hours at the beginning of the next module that you take. Sadly, that starts at 8 o'clock in the morning, 8 till 10, half-hour break for coffee, and then the next module starts. This is what we're going to do this week. Today is the introduction. We'll explain what we're trying to cover over the course of the week and give you some examples to play with. We'll then look at some key software architectures tomorrow that form the basis of these kinds of systems. And we'll look at a range of different potential hardware platforms that you can use in your applications on day 3. On day 4, we'll talk about distributed systems, systems with more than one processor connected together using something like the CAN bus. And we'll also talk about ways in which you can have tasks that interrupt one another on the systems that you're creating, so task preemption. And on day 5, we'll do a case study, which will pull together a lot of the material from the week and give you a chance to work on a slightly more representative system. That's the overall plan. We're going to use C for all of the exercises. I'll talk about why we're going to use that language in a few minutes. We're going to use 2 main targets. An 8051 microcontroller running in a hardware simulator. We're going to use that for the first 2 days. And then we're going to use a more modern platform, a soft microcontroller running on an FPGA, which we'll use for the last 3 days in the module. We'll give you various examples and things that demonstrate that you can run the kind of techniques we're looking at here on virtually any embedded hardware platform. Shoot, here.
What does it mean by soft?
It means that the processor is itself, do you know what an FPGA is? Yep. So the FPGA is essentially a set of logic gates that can be configured implement within reason, well, implement a wide range of possible hardware platforms. So that might just be a set of gates. In this case, we're using the FPGA. We're configuring the FPGA using VHDL, and we're configuring it as a microcontroller, and then we're programming that microcontroller in C. And that's quite an effective approach these days, because it means that you can configure, rather than choosing from a catalog that says these are the available microcontrollers, you essentially build your own microcontroller. If you want to do that, come back in September, and that's what people will be doing then, course of a week. So that's the overall plan. So let's just start with a little bit of history. This is what the world looked like a few years ago. When was the first microprocessor introduced? 1950s. Later. Intel introduced the first microcontroller in 1971. 1971, comparatively late in the day compared with other branches of the engineering profession, very late in the day. Before that, we had to build our systems using a combination of logic gates. Before this, we had to use valves. So systems were created by hardware designers, and you had to create a new hardware design. When you wanted something different to happen, you had to create a new hardware design for each project. The world now looks a little bit more like this. We need a hardware, we need something to run the software on, we need an embedded processor platform of some description, but it's software that's now used to distinguish the different applications. This is a real comment. There are still many organizations which, for historical reasons, still do the software development within the organization. It's still carried out by hardware engineers who've self-taught themselves often assembly language or C programming. And that forms the basis of how the organization does embedded systems development. That sometimes causes some challenges. One of the challenges wherein software has such an important role in these kind of systems is that there's an expectation that changes to software are easily carried out. People assume it's difficult to change the hardware. We built the hardware, it's difficult to change the hardware, but we can easily change the software. So we want to add some new features. Even late in the day, the software guys can change the software. You can argue against that. Software changes are often expensive. It's often difficult to work out what the side effects of any particular change will be. But we need to make sure, one of the things that we'll be focusing on through this week is there's no point in trying to argue against these things. This is the way the world works. If we're going to create robust systems, we need to accept right from the start that those systems have to be created in such a way that we can make changes without having major side effects in the systems that we create. So we're going to start this module by working with an 8051 microcontroller. This was developed by Intel in 1980. It's still available in various sizes and forms. We're going to use it for three main reasons. It's a simple starter processor. It's a good starting point. It's simple, easy to understand the different hardware features that are there. It has very significant resource constraints. It has 256 bytes of memory. 256 bytes, not kilobytes, megabytes, or anything, 256 bytes of memory. That's useful to help people understand the resource constraints that are typical in this environment. It has significant performance constraints. Half a MIP, or 500,000 instructions per second, which compared with the 50 or 100 MIPS performance from a more modern microcontroller is very restricted. Most of you leaving this program will probably not use an 8051 extensively in your day-to-day life these days. But they still have their uses. This is one example from an Infineon design from 2009. And they're using an 8051 microcontroller essentially as a watchdog or as a fail-safe processor in a design. So the main design is running on a 32-bit microcontroller, but they're using an 8-bit microcontroller as a backup device, as a backup and safety and monitoring device. And we'll look at some techniques where that might be useful in the course of the next few days. So although we're primarily going to use the 8051 as an introductory platform for the first couple of days on this module, it may be useful to you slightly more longer term. So this, in summary, are some of the features of the 8051. It's an 8-bit microcontroller. What does that mean?
The bus carrying instructions and data is basically 8 bits.
So the bus carrying, let's just... so we have a 16-bit address bus on this device. What makes it 8-bit? There's not your answer is not wrong, it's just not well defined. Yep.
Yeah, latch is designed for 8 bits to process 8 bits.
Okay.
Yeah, so the instruction set is built upon 8-bit system.
The computational architecture basically deals with 8 bits.
Well, if you say to me 8-bit registers, yep, then I'll say yes. And that's typically what it means, but it isn't particularly well defined. There are things about this that are not 8-bit. The register sizes are 8-bit, the port sizes are 8-bit, but the terms are not particularly well defined. 16-bit processors, 8-bit, 16-bit, 32-bit processors, they have a lot in common, and the terms isn't particularly well defined, but this is usually known as an 8-bit microcontroller, particularly because of the register size. We've got a limited amount of on-chip RAM. What's the difference between a microcontroller and a microprocessor? Okay.
I think it's the other way around.
No, he's right. Every microcontroller, it's an argument I'd accept, every microcontroller contains a microprocessor. It's not a bad argument.
Yeah, so as the microcontroller has memory, and it's designed for better power consumption, while microprocessor just microprocessor without memory.
Not so sure about the power consumption one, but the fact, essentially the general argument with a microcontroller is it has virtually everything you need in the same box. So with a microcontroller, you'd certainly expect to have the memory on chip, and you would expect to have a minimal number of peripherals required to create a complete system. And that would be the broad distinction between them. Many embedded systems are built using microcontrollers. What would you say? You're going to stick your device on an aircraft engine, and you have a choice. So this device is going to be shaken around. It's going to be subjected to extremes of temperature, etc. Would you think you'd prefer to use a microcontroller or a microprocessor, given a free choice? What do you think the potential implications for reliability might be?
Would it be better to use microprocessor to get rid of hardware dependence, or to control hardware dependence on computations, basically? Because if you use a microcontroller, the control hardware might directly implicate or affect the performance of computation, whereas if you use the microprocessor, we might get rid of this.
So I take my microprocessor and I'll have to add some external memory and potentially other components around the outside.
Right.
Or I take my microcontroller and I don't need to add anything else.
Okay.
Let's put it this way. Do you want to put an x86 device sitting on top of the engine? So a typical device you'd get in one of these, a motherboard from a laptop computer. What do you think might be some of the issues that are involved here? I'm not expecting you to necessarily know any of the answers to these questions at this stage, by the way. I just want to start you thinking about some of the problems that are arising. Generally, size is good, yep. Okay, so the size is going to be smaller. Key thing, makes me more comfortable. Any device that's going to be exposed to vibration or extremes of temperature or variations in humidity, would you want to have 1 million solder joints or 5 solder joints? 5. Okay, forget the power consumption. I'm sitting on the top of an aircraft engine. The power consumption for your microprocessor is probably not going to matter. We've probably got bags of spare capacity there. But what I really don't want to happen is bits to start falling off or connections to start breaking because it gets shaken about a bit or because it's exposed to humidity or all the rest of it. So as a general rule, one of the advantages of these guys is they have a minimal external component count, which means in some ways there's less to go wrong. Generally, the stuff that's inside the box is pretty well fastened together. If you have to fasten it to anything outside the box, then there's a possibility that those connections will get broken, etc. So in terms of vibration, response to high levels of humidity, etc., you're probably better off with it in a microcontroller. Although this is a pretty old device, the general spec is pretty much spot on for any kind of processor. We need some on-chip RAM. We need some on-chip ROM, which will probably be flash-based by now so that we can reprogram it easily. We need some I/O ports, generally. We'll talk about all of these factors in a moment. We need a UART. Universal Asynchronous Receiver Transmitter, used for protocols such as RS-232, RS-485. RS-232 is the most common one for these kind of systems. It's a way of hooking up typically your laptop computer or something else and having it talk to your embedded processor. We'll say more about that in a moment. Some counters and timers. These are key parts of any embedded processor. This, apart from anything else, this is what you're going to use to drive your scheduler or operating system. What we're going to do in the next 2 to 3 days is you're going to spend some time working on complete operating systems which are useful for this kind of application. And they will all be driven by these counter timers. And they will also make use of these interrupts. What's an interrupt?
It's basically an instruction that tells the microcontroller to stop carrying out the general flow of instructions and switch to some other mode, basically.
Okay.
A task with high priority is just called, you're going to the microprocessor receive it as a high priority to just perform it rather than just current.
Okay. One way of viewing it, suppose one of these pins is an interrupt source. We could connect a switch on there, generate an interrupt. That would be a way of having a switch connected to this device, triggering some software to run in your application. So an interrupt is a way of having hardware events trigger software activities in your system as a general rule for what's going on here. And that can be extremely powerful and needs to be handled with care. We'll talk about interrupt priorities as we go through. And we need typically some low power, idle, and power down modes. Some of you are clearly keen on keeping the power consumption low here, and we'll look at some uses for these in the course of a few minutes. That basic set of requirements, on-chip memory, some I/O ports, some kind of serial communication device, usually simpler than USB or something, which is much more complicated, some timers, an interrupt source, and some kind of power down mode. That's essentially the spec for a microcontroller. Not just for the 8051, but for a microcontroller that you might want to, any microcontroller that might be useful in an embedded system is going to have these components. There will be differences. These days you'd expect to have a bit more memory, etc. on the system, but the essential spec will be the same.
8-bit microcontroller, but counter is 16-bit.
Yep.
So
That, as I say, the definitions are pretty poor. Generally, the term is used to refer to register sizes, but there can be many other variations beyond that. So this has, part of this system works with a 16-bit address bus, but it's still an 8-bit microcontroller, not viewed as a 16-bit microcontroller. It's not a well-defined term. It is a microcontroller, though. And we know that. One reason we know that is because it's very simple to make this work. That's a complete circuit, complete schematic for hardware design for an 8051 microcontroller. It just needs a power supply, a little bit of a reset circuit, which we'll say more about shortly, and a means of driving it with a crystal oscillator, which is used to drive this system. That's all we need as a set of external components, and we've got a complete system. At this stage, it doesn't do anything very useful at all. We've not even connected up a single I/O pin, so it can't really do anything very much. But the point really here is that we need a very small number of external components to create our complete system using this kind of microcontroller. If you go into a shop to buy, or shop online to buy a laptop, typically look for the highest performance device that you can find for the money. What's the operating frequency of this device? This one's running at 4 gigahertz, this one's running at 100 gigahertz. I'm going to have the 100 gigahertz one. If you're working in embedded space, it's a different world. Typically, higher clock frequency is higher performance, but it's also higher power consumption. It's also higher levels of electromagnetic interference. It also means you need faster memory. If your processor performance is faster than the memory, you're going to need some kind of cache system, which is going to complicate the timing of the operations, etc., in your system. So sometimes in the space we're looking at here, in the embedded space, opting simply for the highest performance is not necessarily the best design option for these systems. And we'll talk a little bit more about this over the course of the next few days. You can, if you wish, add external memory to an 8051 microcontroller. We're going to use, in this module, we're going to run the microcontroller in a simulator for the first 2 days, but you may, if you want to go on and play with one of these things after this module, this is essentially how you can add external memory. There are a number of I/O ports, 4 I/O ports on these small devices. Again, we'll cover enough information about these so that you can use them for the purposes of this module, but every different microcontroller you find has a slightly different way of configuring and using the I/O ports. And the broad level, or key factor here, is to understand in general terms how these ports can be used. So these are digital I/O ports, allowing you to take control of the external world and to read from the external world. There are timers on these devices. These are 16-bit timers. We've touched on this already. You'll need to be aware when you're doing the timing calculations that on the 8051, the timers are incremented every 12 oscillator cycles. We're typically going to be using the 8051 with a 12 megahertz crystal, so most of the operations in the device are going to run at 1 megahertz. We can use the timers to measure the time interval between events, to generate hardware delays, to generate timeout facilities. We'll look at some of these things before the end of today, and to generate regular ticks, periodic ticks that will drive our operating system or schedule. We'll get to that tomorrow. We've talked about what interrupts do. Interrupts are a hardware mechanism to notify a processor about an event. We spend tomorrow looking at how you can begin to create systems using interrupts. Today is going to be interrupt-free. Serial interface on the 8051 is compatible with the RS-232 protocol. One of the sad developments in recent years is that your laptop by now probably doesn't have an RS-232 connection on it. They used to have. This is the standard way of communicating, the simplest standard way of communicating with almost any embedded system. Even the most modern embedded microcontrollers will typically have RS-232 ports on them to allow different forms of connections like this. Typical uses for this are for debugging embedded applications or reading information, etc., from an embedded application in the field, and sometimes programming the devices as well by programming the flash memory. 51s have a power down mode. We've talked about this, which allows you to save power. That's useful. The more important use of idle mode, many of the times on these devices, is that the idle mode can have a very significant impact on the timing behavior. What we will be using the idle mode for from tomorrow is by, let me ask the question in a different way. If an interrupt happens on a processor, when can the processor respond to that interrupt event? Okay, so we've got a processor that's running normal code, and an interrupt event happens.
When it gets to the stage of the code where ISR are.
So I'm running an instruction, and that instruction is going to take, on this processor, two.
That particular instruction.
Okay, and that's the key bit. When that instruction has finished executing, then the processor can respond to the interrupt. And on some processors, there's a variation in the length of the instructions. On the Pentium family of devices, that variation is something like 10,000. A variation of 10,000, factor of 10,000 in the length of the shortest instruction compared with the length of the longest instruction. So if you're trying to work out how quickly the system can respond to an interrupt event, you generally need to know which instruction it was executing at the time the interrupt took place. And as a general rule, that's impossible. You won't have that information. But suppose you put the processor, suppose you can ensure, for example, that the processor is always in idle mode when the interrupt occurs. Then you can ensure that the system's always in a known state, you know what it's doing, and you can then determine how quickly it will respond to the interrupts. That's what we're going to use idle modes for. That will make sense from tomorrow. But that's the main thing we're going to do with idle mode on this course. So we're going to use idle modes to put the processor into a known state so that we are able to determine how quickly it will respond to interrupts. Registers are another key factor in these processors. When people have not programmed embedded systems before, one of the questions that comes up early on is, I've got this set of hardware and I've got the software. I've got this processor, I've hooked up one of the port pins to an LED, for example. Is that me beeping? Who's beeping? Forgive me, it's me. For some reason. If I've connected a piece of hardware to my embedded processor, how do I actually control? If I've got a piece of hardware connected to one of the port pins of my embedded processor, how do I actually control that port pin? How do I make this device do something useful, control the outside world? And the answer is the link between the hardware and software in an embedded system comes through registers. In the 8051, these are called special function registers. And essentially all this means is it's a block of memory at a particular address. And we can read and write to that block of memory. If we write to the block of memory in an 8051 at this address, we'll talk about what the 0x means in a moment, then we will change the value that's output by the processor on port 2. So writing to a block of memory causes, we then leave the hardware to deal with the fact that it's going to change the state of a particular port, and therefore control a particular port pin, and therefore start turning the gun turret, raising the aircraft undercarriage, etc. Will happen as a result of that. Similarly, to read timer values, we'd read from appropriate sets of registers and find out what the timer was doing. To write to a port, we'd write to a particular place. To read from a port, we'd read from that particular memory allocation. That's the key link between software and hardware in these systems. We're going to use the C language to take control of these designs. We're going to make high integrity systems here. Is there a better choice than C?
Yes and no. But if you want to know exactly what it's doing, you want to do it like a machine code or assembly, then it can really control it, but that's no use for making a big system.
Okay, so we could go even lower level than C, and then we'd know exactly what was going to go on in the system. But some of the systems we're looking at here have maybe 1 million lines of C code or code in another language. And if we would actually write them in assembly language, they would be, as you say, mammoth, and it would be difficult to work out what was going on. The assembly language also wouldn't be portable at all. That is, if we change the processor we were going to use, we'd have to rewrite the code probably completely. We could try and go a bit higher level. Have any of you done anything with UML? Limited exposure to UML. So you can try effectively working by designing the systems by drawing block diagrams and then automatically generating code from these block diagrams to meet the needs of your application. That's potentially where the world will get to before all that long. There are other languages, like Ada, which are generally considered better languages for use in these kinds of systems. If in C I can happily create an array of 300 elements, and then on the next line I can write to element 3001, and C doesn't care. Now that, as a general rule, is not sensible behavior in a language that you want to use in high. That's not an error message in the language itself. There is no bounds checking capability built into C. Might be that some of your development tools can pick that feature up, but there's nothing built into C which would prevent you, because you may not know at compile time. So suppose you've got an array of 300 elements, you ask the user to enter a number, and the user enters 3000. If you don't do any kind of checking in there, there's nothing in the language that says that the system won't happily try and let you access an array element out of bounds. Other languages like Ada do those kind of checks. So they do have bounds checking built in. And as a general rule, if you had these features enabled in the language, it would prevent you from accessing that array element. There's also stronger typing in some other languages. So you specify the type of a variable, and there are a limited range of operations that you can perform on that variable which depend on the type. And the type checking rules are stronger in languages like Ada than they are in C. There are better languages. Not very many people use Ada. An awful lot of people use C. This remains a standard language for most kinds of embedded systems. It's more difficult. The Ada language may be better, but it's generally more difficult getting good staff who are experienced in working with the Ada language. So it's a bit complicated. It's all very well having a perfect language, but if you can't get the staff who know how to program in that language, that's a bit of a theoretical advantage. There are a lot of good people programming in C, and that's one of the reasons why it continues to be popular. We're going to use C through this module. Let's look at a couple of examples just to check for the rust that you may have on your C programming skills. Some of you, one of you wears glasses, the rest of you will be immune to this. You go to the opticians, they show you two sets of pictures on the screen, they say, which one looks better, this one or this one? This one or this one? They keep checking different lenses to see until they find a set of lenses that match your eyesight. In your case, which one looks better, this one or this one? This one or this one?
Yes, okay.
Slide 30 or slide 31?
I'm going to go with that.
What's the difference between 31 and 30?
31, you've got a passing constant.
Okay, so what difference does that make?
You can't change it on the fly. Like, for the other one, you can pass anything into the function, but this means you've got to have like pass 30 and then 31.
Okay, so in this one, I could set a debug statement in here that said something like A is equal to 0. And I could do that while debugging, and it would be perfectly valid, but it might end up in the final plane. In this one, I'm assuming that these guys are used to pass information into the function, and that I wouldn't want to change them. And by setting them as consts here, I can't change those values within the function. And that's generally a good thing. Basic rule of thumb, you can't have too many consts in a function header. The more consts, the better in a function header, provided it works. What about this versus this? What type of data are stored in some pointer? What does B store? Don't whisper, shout it. So this type of this is constant integer. What is some pointer storing? So B is storing an integer value.
It's an address, but it's pointing to an address.
Yeah, okay. So some pointer is pointing to, is the address of a memory location
Which stores
an integer. So it's the address of a memory location in which we can store an integer. What's the difference between this version and this version?
the address is constant.
Let me ask another question first then. What am I doing here? Let's stick with this version. What am I doing here?
You're changing the value that's at that pointer.
Okay, so I'm basically saying Yeah, change the contents of the address here to be equal to square 1 plus square 2. I can still do that here. Why would I argue that the second version is better?
I suppose it's what you said before, you can't change that then. You can't change where some point to point.
So the risk otherwise would be, in this version, it's possible that somewhere within this function I could change the value of some pointer, and therefore when I did this I'd be writing to an unknown memory location, potentially overwriting the operating system or doing something else in the system that was highly undesirable. The flexibility of C means that we have to handle the language with care, because the side effects of doing this, so basically the language lets you say, here's an address, write some information into that address. And you need to be absolutely sure before you do that, you actually know where that information is going. So this is saying that we cannot change the address. What about this?
Address and the value both remains. The data, the address where the data is stored and the data itself both remain the same in this case.
Okay. So tell me what you think that has in common with these.
Fixed data.
Yep. In concept, they're very similar. I have to access the data slightly differently because in this case, I'm talking about an address. In this case, I'm actually talking about the data themselves. But this time, I'm referring to the data by address directly here rather than by name. So here, doing the same thing though. If you like, this is a read-only pointer variable. So in this one, we're saying we can't change the address. So this sum pointer stores the address at which an integer value may in turn be stored. And we're saying here we can't change the address, but we can change the contents of that address. And here we're saying we can't change the contents of the address and we can't change the address itself, but we can still read the value that's passed through. What about this code? If I have an array, let's say I've got an array of integers. I've got 1,000 integers. That array is going to occupy a block of memory, which is 1,000 times the size of an integer long in most cases, 1,000 times the size of an integer long, and starts at a particular memory location. Suppose I've got a function. That's a set of code, simply a set of instructions. In fact, at the end of the day, just a set of binary data, just like my array of data. So I've got my function. That's a block of data. Starts somewhere in memory. When we're doing this, we're saying this is the address in memory at which an integer starts. That integer might be 100 bytes long. And this is the address in memory at which that integer, the information relating to that integer begins. Here, what we're doing is we're working with what are known as function pointers. So these are data pointers. These are function pointers. So in this case, what we're working with is the address in memory at which a function begins. This is something that most people who are working with C in a desktop environment never use. When you're working with C in an embedded system, it's very frequently used. This is the core of the way that most operating systems are created, and even simple schedulers that are used to run tasks, which we'll say a little bit more about in a moment. And we'll be using this approach from Wednesday onwards to build some of the simple operating systems that we're working on at that time.
How is using function pointers better than using functions themselves?
Ask me that on Wednesday. It can become quite an elegant way of having the system select from a possible set of functions that it might want to call and call one of a particular set of functions depending on certain criteria. So for example, after 300 milliseconds, the system has a table that tells it after 300 milliseconds it should call this function. It becomes, using this gives you quite an elegant way of creating that code. Otherwise you end up with a large set of switch statements typically, which are difficult to maintain. But we'll look at that. We'll look at why these are useful a little bit later on. Let's begin to look at what is actually happening in terms of the software we put in these systems. None of you are old enough to have had done anything with DOS-based computer systems. DOS was great fun. If you had a spreadsheet in a word processor, for example, and you changed your printer, with a DOS-based machine, you needed to get a new printer driver for the spreadsheet and for the word processor. And if you had 15 different applications running on your machine, you needed 15 different sets of upgrades for the word processor, spreadsheet, and whatever else, which seems daft by now. That's the way the world works. You didn't tend to buy new printers all that often because it was such a hassle. By now, the operating system on a modern desktop or laptop design, this provides the common code for graphics printing, file storage, etc., which is shared among the different applications that are using that system. And the desktop code you tend to think about by structuring it in this way. If you're working in C, you tend to think, okay, I've got function 1 which calls this calls function 2 and 3, and these in turn call these different functions in the system. That's the way you would typically put together C code. This is a typical architecture for the code used in a deeply embedded system. So this is our main function. What happens here?
Sequential calling of functions.
So what does the while one do?
Calls
Okay, so while one means while true means basically loop forever. So we call this function, read the retired temperature, get the temperature in the room, control the boiler, and we've got a central heating controller system. So we initialize the system, do this, and we get to that statement called return 1, which we'll look at in a minute. Suppose I change that code to that.
You get to return 1 a lot quicker.
Gets return 1 a lot quicker, so it's faster. Yeah, it's a good solution.
It just wouldn't do what's inside that. You wouldn't have a central heating system.
Okay, so we don't do that. Then what happens?
Your system exits. Return 1. That's it.
Okay. Then what happens?
you've already exited the program.
So in this kind of system, there is no operating system. There's no operating system. This is all of the application code. There's only one other piece of code here, which is usually called startup code in the design, and that's a little bit of assembly language wrapper that sets up some stack, etc. in the system. We'll look at it in one of the examples. Sets up some stack and basically calls the main function. And that's all that happens. So we've got literally a few lines of assembly language code, set the system up, call main. Then we run this lot, and if we've got as far as this and we step over here, what happens?
Basically shut down.
You live in a tidier universe than I do.
Would it just be reading random memory, whatever is past that?
Okay, so what we're actually doing this on then is we're doing this on our standard desktop development environment. Yep. And the code we used last time, this code we stored in Flash last time, is the one that fires the gun turrets. And that code is still sitting in memory. And what happens, unless you've taken particular efforts to avoid this, is that's while zero, we go through here, we exit this, and we just keep going through memory. Processor doesn't care. It just keeps executing the instructions that it finds in memory, left over from the last application that you created.
So how do we erase once we exit the
Well, if you erase them, what would that do?
No, how do we...
So let's go with your first one, even if it may not be quite what you meant. But let's suppose we erase them. So we're now all filled with zeros in memory. That's probably a NOP instruction, no operation instruction for the processor. Not always, but typically that's what it's going to be. So that will be interpreted, doesn't care. There's something in there, and it's going to do its best to interpret it. And if it can't interpret it as a correct instruction, it will probably generate an exception which says invalid instruction, and it will jump to somewhere else in memory and keep executing the code that it finds there. So your problem may not be solved unless you've handled that correctly. So this could be doing anything in your system. And you need to make sure, how would you avoid some of those problems happening? First thing you want to do is to make sure, well, try and make sure in here that that can't happen. Probably what you also want to do is try and make sure that your assembly language startup code has itself a while one loop in it, so that if you ever return from main, it just sits there in a while one loop, just executing, doing nothing, because that's probably all that it can sensibly do under these circumstances. If you did have the memory filled with zeros, if these were interpreted as no operation instructions, so basically do nothing, the system would fly through memory and would come back up and would start running this again. It would wrap around and would keep running this periodically. Exactly how long it took to get back here would depend how much memory you had, how quickly the processor was running, etc. But almost certainly, this would be bad news. So one of the things you have to understand early on in this process is how this is going to work and the impact that all aspects of the system are going to have on the way that your design operates, even if it doesn't operate quite correctly. Most of the systems that we produce during this week are going to be created using functions like this. These are going to be our tasks in the system. So most of our system will be built from void functions, and the data transfer between these tasks is going to be carried out using global variables. Now, if you've done anything with desktop programming, you'll be doubting my sanity right now. So this is about high reliability embedded systems. We've just talked about how you can control the data transfer between tasks by doing appropriate things in the function headers. What we're actually going to do to transfer data between the tasks in our system is we're going to use global variables. Because at the end of the day, that's the only approach we will have. If we go back a few steps, this is what a desktop program looks like. Set of function calls, one function calling another. An embedded system looks a bit more like this. We have what are apparently a set of isolated tasks. We're going to implement these tasks as void functions. So they're still going to be implemented as functions. But they're going to be called by our operating system at particular points in time. Or they're going to be triggered by other interrupts in the system. They're not directly called. We don't any longer have this nice clean hierarchy here where we can say one function is going to call the next, etc. Instead, our architecture looks like this, and we don't have the same clean way of saying the order in which particular tasks will be called. So we end up having to find an appropriate way for representing these tasks, and we do so with void functions, and we pass information between the tasks using global variables. We'll see more about that over the course of the next few slides. You can still have controlled interfaces between tasks calling other functions. These might be driver functions, etc. So we can still use this as a means of transferring information between from one task to call another function. But in most cases, these tasks themselves will be created using void functions. What time do we have? Right, just before I start using switches, I'm going to suggest, I've been blathering for about an hour, I'm going to suggest we break for 10 minutes and we'll come back and carry on. Right, so gentlemen, virtually every embedded system has a switch interface. So we're going to spend about 20 minutes looking at how you can connect switches to your embedded system. Lots of possible options. Virtually everything has them. Different switch interfaces, keypad type interfaces, and also the kind of mechanical switches that you might find in an industrial setting, obtaining information from the environment, all based on some kind of switch input. In the 8051, we control the ports through appropriate special function registers. There's a very simple I/O circuitry in here. Other more modern microcontrollers have more complicated I/O circuitry. In the 8051, it's very simple. If you want to use a pin on a port as an input, you must write a 1 to it before you use it as an input. That's all you need to know in terms of using these pins. Other microcontrollers are set up. You can configure the pins as input, you can configure the pins as output through a different combination of techniques. In the 8051, this is how you do it. So this is how we would set port 1 up for input. We'd write P1 is equal to, and we'll come to the 0x in a minute, we'd write 1s to all the port 1 pins, and then we could read data from that port. It's straightforward. This is how we can do so in the simulator that you'll be using in the exercises over the course of the next few days. So this is the Kyle simulator. Kyle's part of ARM these days. This is how we would write 1s to those pins, and this is how we would write 0, 0, 0, 1, 1, 1 to the particular pins on port 1. If you did this, you'd see the outputs in the simulator. As most of you, I hope, know, 0x is notation for hexadecimal in C, and this is just a reminder of the conversion. So base 16. We can set the system up to read and write bytes using the architecture that we've used here. Reg 52, oops, excuse me. Reg 52.h is part of the Kyle environment, and that's what tells the compiler what P1 means. So basically it gives you the, defines the SFRs so the system knows what's actually being required here. So here we're setting up port 1 for reading. We're reading the values and we're copying the values to port 2. There's port 0, 1, 2, and 3 on these devices. And again, in the simulator, you'll see the system operating as shown here. So this is how we can do the same thing using individual pins rather than complete ports. S-bit is a variable declaration. What's the difference between a declaration and a definition in C?
Defining new type of variables based on existing variable types and variable definition. And variable declaration is declaring a new variable with an existing.
Yes, but the other way around. One consumes memory. Which one consumes memory? Definition. Definition consumes memory. Declaration, that's a declaration. It doesn't consume memory. It's telling the compiler, in this case, it's saying there's part of this SFR, the port 1 SFR in this case, has already been defined. It's an existing block of memory. This is a declaration which is saying, I'm not consuming any new memory, I'm just giving you an alias, if you like. I'm just giving you a name for, another name for that part of memory that you have already allocated. And that's the difference between a declaration and a definition. You typically use a declaration to tell the compiler there's a variable called x that's of type ABC, and it's been defined elsewhere. Somewhere else in the program it's been defined and memory has been allocated for it, but all you need to know at this stage is that that variable exists and this is the type that it has.
So P1 has been defined in Reg 52.
P1 has already been defined, is already effectively in this case it's defined as a particular memory location, and the particular memory location that's associated with will be made clear in Reg 52.h. So that's how we can read bits. These are the bitwise operators. This is there to refresh your memory and for you to review. So this is a little bit of C for you to play with, how you do the various operators, how you implement various operators and what they do in C. I'm not going to spend time on these. This is how you can take, working with the Kyle compiler, this is how you can take a couple of functions and read a particular bit and write to a particular bit using this compiler. So this is allowing me to read from a particular pin on port 1, and this is allowing me to write to a particular pin on port 1. These are here just as examples as to how you can actually use the various C operators to achieve this effect. So I'm going to let you digest those in your own time. We now know how to read and write to port pins, not complicated, using C for the 8051 microcontroller. To read a switch requires one more step. When you press and release a switch, what we're going to do is we're going to connect the switch typically between a port pin and ground. When we press the switch, the voltage read at the port pin will be 5 volts or 3.3 volts, depending on exactly the logic of the system we're working with. When we press the switch, the reading will be 0. When we release the switch, the reading will go back up to 5 volts, logic 1 again. That's the theory. In practice, the switch bounces a bit. So when you press it, it takes a very small amount of time to settle down into that state. It's a mechanical switch, and when you release it, it similarly bounces. Happens every switch you've ever used. What kind of period would that have to be for you to notice it as a human being?
500 milliseconds. 1 second.
500 milliseconds if you were about 150. You would probably, your perception threshold would be shorter than that if you were a bit younger. At least down at the 50 milliseconds, 25, 50 milliseconds level, you begin to work out that something was happening here. If an event visual event takes less than about 50 milliseconds, you probably won't notice. It's important to know because you need to know that information when you're creating user interfaces. So if you set that to be about 20 to 50 milliseconds, most users won't recognize any flicker or anything in the display. But the microcontroller will. As far as the microcontroller is concerned, that's the switch being pressed and released 3 or 4 times. And if you don't do something to do what is known as debounce the switch input, if you try and count the switch presses, that's what you think is happening. That's what the microcontroller sees. You'd view that as 1 switch press. It would view that as about 20 because of the switch bounces. So how do we deal with this? Let's deal with one other question before we look at that. I've got 2 options for the input interface to my next system. I've got this switch, which is a latching switch. So if I push that down, it stays down. I've got this push button switch. It could be push on, push off, or it could just be a single switch, which is just push it on, a little LED goes on and it stays on, push it again, the LED goes off and it's off. Which type of switch would you think would fill my heart with joy? And which type of switch would worry me if you put it on your application? It's a reliable system.
It all depends if the latch is able to eliminate bouncing.
No. This, in fact, is less likely to have bounce because of the nature of the switch, but bounce isn't the issue. We can deal with bounce. I'm not worried about that.
I reckon the left one. I don't know why, but it's just because it's either on or off. Like you've got one choice. There's only one thing to go wrong. All that kind of thing. I don't know.
Okay, so we've got 1 vote for this one. I want everyone to be brave here. I want everybody to vote. This one or this one?
I don't know. Can I split my choice?
Okay, so let's have votes. This one or this one?
Latch.
So votes for this. Yay! Everybody votes for this. Votes for this. Yay! My vote, this one, every time. Why? Because I am, and you need to be, a control freak. You need to be in control. Suppose that's putting on the nuclear reactor. So I click the switch down, nuclear reactor's on. Yep. But suppose the nuclear reactor now overheats. And it goes off. So at fail-safe mechanisms, it goes off. But somebody walks into the control room, the switch is down, therefore the nuclear reactor is on. And they make decisions based on that. On this one, if the nuclear reactor goes off, I turn the LED off. I turn on the off LED, whatever. My system has control of this. In this case, I've given the switch control. That's just an interface here, but it's significant. It would be difficult to have this, which gives you such a clear indication of the system state. It would be difficult to update this to reflect real changes in the underlying system state. And therefore, I'd argue it's probably a bad choice. This one, I can update the interface easily to reflect changes in the underlying state if they happen through reasons that are nothing directly to do with the switch. But I can't do so with this. So I'd argue that for this one, I've got more chance of keeping the interface and my system in sync, and this is likely to prove a more reliable option. We'll argue about the underlying approach a little bit more with a couple of other design examples over the course of the next few days. So let's go back to the switch debouncing. Let's start with the simplest possible way of doing this. We're going to read the relevant port pin. If we think we've detected a switch depression, we're going to wait for the debounce period. In this case, 20 milliseconds or 50 milliseconds for the switch to bounce will be more than enough. We're then going to read the pin again. If the second reading confirms the first reading, we assume that the switch really has been pressed. So it's not going to bounce for any longer than this, but we're not going to just basically immediately check, is it pressed, return. We're going to basically check to see whether it's pressed. If we think it's been pressed, we wait for a little while for the switch to settle down, and then we return the value. It's not perfect, but this will get us started. So we can turn this into code here in this form. So who wrote this? This is appalling. What's wrong with that line of code? If switch pin equals 0. If you wrote,
it might be like 0.0009.
that's probably okay, because it's probably going to be, it's a digital input, it's not an analog input, so it would give me a value of 1 or 0 depending on whether the switch was pressed or not. That bit's probably okay. But if you wrote code for me like that, I'd sack you. And this is my example.
Would you just use the exclamation mark and go equals 0 and make it a predicate?
Nope. That's not the... What I'm concerned about is the 0. So the 0 is making some assumptions about the way that my switch is pressed. My switch is connected to the system. It's assuming, in this case, that my switch is connected directly. So I've got my switch, I've got my interface, it's going like this. I've got my switch connected like that to ground. It's assuming that. But suppose that's not what I do. Suppose I put an optical isolator in here or something and invert the switch connection. So sometimes, as far as the device is concerned, depending on what interfaces I put on the switch here, or depending on what other hardware is out here, 0 may not mean switch pressed. Could be 1, depending on what goes on out here. And I don't really want to get confused by that. So that would be much better to be a constant that said something like switch pressed than to be a 0. Because then I've got more flexibility and there's no ambiguity when I try and read it. I probably only have to change it in one place, so I'd much rather see this in real code if switch pin is double equal switch pressed. And that would be better, in my view, in there. Ignore that for a minute. Assume the wiring is correct, then we're going to go into a delay loop. We'll look at that in a moment, and we're basically just going to wait for the debounce period, which is going to be about 20 milliseconds here. Then we're going to check if the switch is pressed again, and we're going to set our return value to be equal to switch pressed, and we're going to then return the value from the function here. It's not perfect. There are 1 or 2 flaws with this, but that's not a bad starting point for our switch press code. One of the problems with it is that if I keep the switch pressed for a while in this version, it's going to return. It's just going to wait for the debounce period, then it's going to return. And that in itself may not be what I want, but we'll solve that problem in a minute. That's not the main problem here. So that's our starting point for a switch press interface. Let's turn that into our first application. These are goats going into a milking parlour. We're going to count the number of goats here. Every time the goat walks through along this aisle into the milking parlour, it presses a switch, a mechanical switch, and I think it says optical here, but anyway, we get a signal that looks like this when a goat goes past. And I want to know how many goats have gone into the milking parlour. Here's our code. So we've got some constants up here. We've got our function prototypes. We've got our main loop. And it looks much the same as before. We have some initialization in here. We check the switch, and we display the number of goats that we've counted in the switch each time we go around this loop. We initialize the switch interface, which means that we set the switch pin to 1 so that it can be used as input on the 8051 microcontroller. We then have our switch get input code here, and we've made one slight change in this version of the switch input code. Now we check to see whether the switch is pressed. We wait. If the switch is still pressed, then now we wait until the switch is released before we return from this. So if the goats take longer than 50 milliseconds to walk through, it won't matter. So essentially, it'll only be once the switch is released again that we will return from this function. This will work. Still don't like this code, and by the end of this session we'll have created a better version, but that's a starting point. That will debounce our code, and it will work. We simply display the values that we've counted on a particular port. That bit is straightforward. What about this? Okay, so it's a nested delay. What's it doing?
Nothing. Basically just stopping for that time. Incrementing variable.
Okay, so we're just burning CPU cycles to give us a delay here. How do we determine these values? So this is a 12 megahertz 8051, and the delay in milliseconds is roughly set by this parameter here, delay milliseconds, and this number is 120. Is that significant? Does that match that? No. Pure coincidence. For this kind of delay loop, it's almost impossible to determine the values theoretically. The only way of determining these kind of simple loop delays is by running them on a simulator or on the real hardware. But that's the simplest way of setting up, in this case, a delay of approximately 1 millisecond in this system. So that's all we're trying to do here, and we're going to run that for our debounce period of about 30 milliseconds in this design, and we've got our first complete application. So that comes back in here. We're using a 30 millisecond debounce period, and we're waiting in that function until the switch is released. Every time we every time we return from this function and we're told that the switch is pressed, then we increment the count and we display the count on the one of the ports. There's no error handling in here. Once the count gets up to 255, it's just going to wrap around, but it doesn't matter for our simple example. So we've got first simple application put together in this form. If you're inclined to do so, you'll find this on the CD in the back of Embedded C, and you can display the results in the simulator. This is what the switch hardware would look like. We're going to use a simulation for this. Again, the particular hardware requirements you have will vary with a particular microcontroller. These are just in case you want to fill in the gaps for the 8051. This is typically how you would connect a switch interface for an 8051 microcontroller. You would simply take the switch and connect it between ground and the port pin, and that's all you would typically have to do. In some cases, for port 0, there are no internal pull-up resistors. if you don't have pull-up resistors on a switch, this is in effect what you will see. You will always read 0 from the switch without a pull-up resistor in the architecture. So if you're going to use port 0 on an 8051 microcontroller and you want to wire it up, you need to add an external resistor to pull the port pin up. That's all we're going to deal with on here. This is simply there for completeness. You won't need to use this week. Why do we use C and not C++? C remains a standard for, if you've done any programming, the general argument is that object-oriented languages, C++, Java, etc., give you advantages when you're creating larger systems. C remains the most popular language for embedded systems. One of the advantages of object-oriented designs is it's claimed that an object-oriented approach, structuring your system in terms of classes and objects, makes it easier to reuse the code between projects. Using C++ is not common, not as common in embedded systems. What we want to try and do is find a way of gaining some of the advantages of object-oriented approaches while still working with the C language. And that's how we're going to structure most of the examples that you will see on this course. So people argue that OO is great. This is one of the ways in which C++ code and C code varies. These are effectively the equivalent operations in C on the left and in C++ on the right. What an object-oriented approach does, it allows you to define a particular set of interfaces, a particular way of controlling access to data in your system. So in this case, we have data which are encapsulated or even embedded inside our class. And the only way we can change the values of these data are through these two particular member functions. In C, the equivalent is that we effectively have public data and we can change the values directly. We want to gain some of the advantages of an object-oriented approach, but still working with C. One of the reasons that people don't use C++ in these kind of systems is some of the mechanisms for doing things like this form of protection may add additional overheads to the system, which are considered undesirable. If you think back to our last GOAT example, we wrote all of the code in a main function. That's not going to be, that makes it difficult to reuse the code in multiple systems. What we're going to do now is look at how you can split that code up into and split it across multiple modules, which give you many of the advantages of an object-oriented approach while still sticking with C. I'm just going to look at some of the parts of this because on past form this causes people confusion. If I'm honest, the bit that people find most difficult during the course of this introductory week is the C. The bits we do about the embedded systems and everything else are usually less challenging for people. The bit that holds people up is the C programming in the exercises. And this is one of the bits that confuses people. We've set the system up so there are some public member functions, publicly accessible functions for particular modules. We take it back a chunk again. We're going to set our system up into a set of modules. We're going to break up the program code so it's no longer written in a single main function, but it's written in a set of modules. So our switch interface would be a separate C file with a matching header file for the switch interface, for example. If we wanted to reuse that code in a different project, we would simply need to copy this .c and .h file into that new project. Similarly for the operating system, for a serial interface, etc. To build our code in this way, we have a set of public member functions. These have their prototypes in the header file of the system. We have some private member functions. These have their prototypes in the C file. The private member functions are functions which are only used by other functions within that module. They'll not be used by the external world. We have public constants, also in the header file. We have a limited number of public variables which are used to transfer data between different modules in the system. These are defined in the C file without the use of the static keyword. So the main way we're going to transfer information between these different modules is through the use of global variables which are defined in the appropriate module. So these public variables are defined in the C file. And we'll look at the use of static and extern as keywords in a moment. And there'll be numerous private constants and private variables also defined within the C files. These constants will only be used in this module or in this file. This will make sense in due course for those of you that haven't done as much programming. This is one overall example of the way that this is intended to fit together. We've got some public function prototypes in this module example. We've got some public constants. The C file itself has some public variable definitions. These are data which will be used by other modules in the system. And private function prototypes. These will only be used by other functions within this module, and some private constants, which are only used within this module. We've got some private variables, again, only used within the module, and then the function definitions themselves in the structure. We use another feature, what we call a project header file. Each of the projects you see will have a main.h file, and that has the information which is common across the project. So we use what we call a project header file. It's usually implemented in main.h, which stores things such as the oscillator frequency, which is used all the way across the application. So this is an example of that. An example main.h file. What does this do?
Make sure it doesn't include the header file more than once.
Make sure it doesn't include the headers more than once, which can be problematic in the program. So when you see that gobbledygook at the start of the files, it's because these files may appear in different programs throughout the system, and we're trying to make sure that they're only included once in any particular C source file. So we've talked about this. This is the reg52.h file. That's the Kyle file that has the register details, etc. in it. We have the oscillator frequency used in this system. Information about that is stored here. Why is it UL at the end?
Unsigned long.
So what would happen if I didn't?
It would be signed, so you'd have the minus side, so you don't want minus frequency because that's not really practical. If you didn't use the long, it could be too short. You might try and put it to just an integer. Or
Okay, by default it would assume it was an integer, and it could be truncated, or we'd end up with an inappropriate value resulting from its interpretation of that constant. So we're explicitly labeling it as an unsigned long to avoid that problem here. Remember, this is a small system, an 8-bit microcontroller, so even at this comparatively small constant length, we might otherwise have problems. So we're including that information, and we'll look at some examples where we actually explicitly make use of that. But apart from anything else, in your system, why would I want to know that? Let's assume we never actually use that information automatically in the program. It's still useful to have it here. Why?
Gives you an indication how long an instruction will take.
Yep.
Anyone who needs to maintain your code can just look at this and get all the...
And why would it matter? We've looked at one example a few minutes ago as to why it would matter explicitly what my oscillator frequency was. Just for the delay code, for example. So the delay code, we just put some magic numbers in which said this will give you a 1 millisecond delay. But if somebody came and ran this on a 33 megahertz crystal, and I'd assumed a 12 megahertz crystal, all those assumptions would be invalidated. So if nothing else, this should, in the code, specify what the assumptions are. Somewhere, we need to tell the user what we're assuming, because the software, as a general rule, has no way of knowing what the hardware environment it is it's running in. You have to provide that information. Similarly for this, different 8051 microcontrollers require different number of oscillations per instruction. Traditionally, this was 12 oscillations per instruction. So you had your 8051 microcontroller, 12 megahertz external crystal. The system was actually running at 1 megahertz. So it took 12 oscillators cycles before to run one machine cycle. That now varies. Some devices take 12, some take 6, some take 4, some take 1. And again, this is crucial, because if you don't know what assumptions have been made, the timing may be badly out in your application. What about these things? So here's an easy question. How long is an integer? How many bytes is an integer in C? 2 bytes. Nope. Nope. Depends. Yep. How do you choose? So basically, it varies with the different hardware platform that you're using. How do you choose the size of an integer when you're creating a C compiler for a different platform? Might be 24 bytes. Might be 1 byte. How do you choose? You choose it based on the data size that that processor can most efficiently manipulate. If you put your compiler together properly. So it will be related to register sizes or bus sizes, etc. But you'll choose that when you're creating the compiler to give you a data that will be most efficiently manipulated. Sometimes people assume that the 8-byte data, the smallest block of data, will be most efficiently manipulated in their design. So they've got a large, powerful machine, and they assume, okay, if I set this data to be 8 bits in size, it'll be manipulated most efficiently. It'll be faster if I make all the loops, all the for loops have 8-bit variables. Often that's wrong. Often, most cases, the for loops will be most efficient if they're implemented using integers, because that should be how the compiler has been put together, even on an 8-bit device. So why do we do this then? Aliases. So in almost all of the code examples I show you from this point in time, you'll never see unsigned int. 8051 is most efficient at implementing unsigned data, and that's how this thing has been set up in most cases. But you'll never see me write code, rarely see me write code that says unsigned int x. Instead, what you'll see me write is t-word x. Why? Variable. Looking for one word here. I'm looking for one word answer. Portability. It should be, if I take my code and I move it to a different environment with a different compiler with different sizes of integers, in a perfect world, all I'll need to change is in main.h, just change these type defs to try and get as close as I can to my t-byte, t-word, t-long variables which match that compiler. And I shouldn't then need to go through, if the integer size varied from one compiler to the next, I would otherwise have to go through potentially and change virtually every line of code or a huge number of lines of code in the program. If I do it like this, all I have to do for the compiler is change what t-word means, which may be one line. It doesn't always work terribly well, to be honest, but it's often better than nothing. Really depends how big a step you're doing in it. So you'll see something like this. Interrupts we're going to talk about more tomorrow, but they're also set up in here. The other thing we do in the code examples that you'll see, and we could argue for and against this approach, but this is what you will see. The different examples that you'll see, all of the port access for all of the different modules in the system is all wrapped up in a single file called port.h. So in the projects you see, there's one file called port.h, and that defines what every module in the program uses, which port pins are used in all of the modules in the program. Again, it's intended to try and avoid conflicts there. That's the only other part of this that you need to understand. I'm not going to do this in any detail at all. This is taking that approach. There are different ways of building these systems. We're not arguing about that. You just need some way of structuring your system to try and make sure it's easy to use. This is the approach we're going to follow for the examples over the next few days. So this is the goat counting example revisited. Does exactly the same thing. It's just a little bit better structured. The main.h file is exactly as we've shown you. The port.h file sets up, simply lists all of the port connections for this system. This is main. And this is typical. Main file will typically be about a page or so long. Virtually nothing in there. Everything else is broken off into other modules. And it will typically, even in your most advanced systems, there's going to be a while one loop in there. There's going to be some initialization. And there's going to be a while one loop in here doing some of the work. We'll change this a little bit by the time we start using interrupt handling tomorrow. But the overall architecture will remain the same throughout the week. Some initialization and an endless loop in which some things are carried out. So we've got a header file that has some public function prototypes and some public constants for our switch function. We're initializing the switch. This is the switch .c file. The switch code is exactly the same as before. It's just now separated off into its own module. The display also has a header file, a .h file, and there's a corresponding C file for that. Again, very little happens in this display module. Delay loop operates in just the same way. Okay, that's the end of the introduction. So the module really starts here. We have a few slides to really begin this module. What we're really interested in is real-time systems. What does real-time mean?
Actual implementation and computation is done while the system is running.
Okay, don't like that much. What does real time mean? Fast? Real-time system is fast, right?
The actual temporal implementation matters more.
Okay. So it has to be fast?
You can't wait forever for a particular signal to come through. It has to be at a particular time for it to work.
Okay, so I like that much better. So the key thing is, with most desktop systems, we largely ignore the concept of time. With most embedded systems, time is absolutely crucial. You put your foot on the brake, and it takes 3 seconds for the brakes to engage. Even if they engage perfectly, it doesn't matter a jot, you're probably dead. The point is, when you put your foot on the brakes, you need to get the right result, and you need to get the right result at the right time, or it's completely useless to you. So it's a system in which the time at which results are created matters often as much as whether the results are themselves functionally correct. Some people like to split this between hard real-time systems and soft real-time systems. And then hard real-time systems, they say, we need to guarantee that the processing will meet all deadlines, and in soft real-time systems, we can tolerate some missed deadlines. These are common definitions. I think this one's almost useless. I think it's either a real-time system or it's not. You either need the things to meet the constraints or you don't. That's not soft real-time, that's just not real-time. It seems to be a contradiction to me, but that's the way the world views these things. And there are lots of different ways in which that applies. If you're building a control system, you need to be able to guarantee that you're going to be able to read the sensors precisely every 10 milliseconds, plus or minus a microsecond, perhaps. You're going to need to generate the control output every 10 milliseconds, plus or minus a microsecond, perhaps. If you get it wrong, the passengers are first going to get airsick, and second, they're going to die. It's not good. So running as fast as possible doesn't mean anything. It does not mean it's real time, and that's the biggest confusion that happens over these things. And you'll have people saying it's a real-time database system, and what they mean is it goes as fast as we could get it to go in the time we had available to get it tweaked. It doesn't mean anything at all. You need to be able to guarantee the operation. You've got a satellite system circling the planet that needs to download data every 24 hours, and it needs to be able to generate that data precisely every 24 hours at exactly the right point in orbit, etc. That can be a real-time system, even though it's only happening once a day. And it's a not uncommon requirement. So this is the time when we talk about features which fill my heart with joy. I've got 3 options for you. You can create a set of tasks where the system has minimal best case execution time. So we're starting to worry about timing now, and we're starting to worry about the components in our system, the tasks in our system. And we've got 3 options. Minimal best case execution time. So at best, when it runs, we want it to run as quickly as possible. Or minimal worst case execution time. So at the longest time this task takes to run, we keep that to a minimum. Or the best case execution time is equal to the worst case execution time. Which do you think? I walk into your organization and you tell me, we always work on this one, or this one. Now do you want to fly our plane? And with one of these, I'm much more likely to want to fly your plane. Which one?
Worst case, sure.
Worst case, surely? Mm-hmm.
Is it the last one?
The last one is the one that fills my heart with most joy. I've got to design my system based on that, or based on the worst case execution time of the task. So I'm going to create a system based on a set of tasks. And these are the components we're going to build it from, typically from C functions. And I need to know what the worst case time it is to execute each of those tasks. If I don't know that, I can't build the system. Because if I don't know how long it's going to take, how can I possibly schedule it to run every 10 milliseconds or something? Maybe it takes 20 milliseconds to run. That wouldn't make sense. I need to know how long all these tasks are going to take to run. So I'm going to need to know that. If I know that, but because effectively, when I know that, I've got to allow, so these tasks run, at worst it takes 20 milliseconds for this task to run. So I've got to allow 20 milliseconds every time that task runs, or I don't know how the system is going to behave. But since I've got to allow that, wouldn't it be better if the task always took 20 milliseconds to run? Because if it always took 20 milliseconds to run, I've got to allow 20 milliseconds anyway. And if it always takes 20 milliseconds, suppose I run it, and it takes 20 milliseconds to run, and then the next 3 times it runs, it takes 3 milliseconds, 4 milliseconds, 6 milliseconds, 7 milliseconds, and so on. Is it running correctly? I don't know. I know it's met the criteria, which is that it mustn't exceed 20 milliseconds, so I have to assume it's running correctly. But I don't know. If I have to allow 20 milliseconds, let's make it run for 20 milliseconds. And if it takes 19, I know something's wrong. So any variation would then be a clue that something was gone wrong with it.
Is it always possible to ensure that? Isn't that tricky to ensure that?
It's, as we discover, virtually nothing we do this week is entirely straightforward. This is easier, but sometimes there are benefits to be gained from doing that. From balancing the code, because then it makes it easier to predict when errors have occurred. So this is the approach that's followed in most desktop systems. Average case or best case execution time is the only thing that people focus on. And they'll just tell you that the average execution time, our average execution time is X. And in a real-time system, that's of virtually no value to me. Because the average, it may be the average, because it happens, it takes 1 millisecond every 1,000 times, but for 999 times out of 1,000, it takes 1 millisecond, but then it takes much, much longer time the other times, and that could be enough to crash my plane, etc. So average times are no use to me. We need to know some of these values, and we'll talk a little bit more about why best case times equal to worst case execution time might be a good idea over the course of the next few days. So let's go back to our switch reading code. Keep some of those things in mind. And there are 2 problems here. This I don't like. I've got a software delay here for my debounce period. This I don't like. What's really wrong with that? Overall, we're wasting a lot of CPU time in this code. We'll deal with that tomorrow. Laying that aside for a moment, the real horror of this, that causes me concern because it's difficult to know exactly what the delays will be. That's frightening. Anything that looks like that is frightening. One example, why? Suppose the switch is broken. Shorted, broken. Not connected correctly. Suppose somebody else has messed around with the initialization operations for that particular port pin without me realizing it. I could be sitting here forever while my plane just tumbles out of the sky and into the ground. Because this, the problem with this, even if the switch doesn't always works correctly, who's in control?
Code.
No. No, no, no. The code's not in control. That's the problem. I'm not in control. That's the real problem. Yep. Who's in control? The switch. the switch is in control. The idiot who's pressing the button, the damaged switch connection that's running over the top there, that's in control. This, if you want it more formally, this does not have a bounded execution time. This has a potentially, it's an unbounded execution time. It's impossible for me to specify what the worst case execution time for this function is, because it depends on factors which are entirely outside my control in this system design. And therefore, it's explicitly not safe to fly. Or to do anything else. Even in a washing machine, I'd be concerned about this, because I'm quite likely to end up with water all over the floor or whatever else, because essentially it's not a robust approach to building the system. So let's deal with both of those problems. Our 8051, every processor used for embedded systems has built-in timers. We can use these to create hardware delays. The details of the individual SFRs are here. I'll let you peruse those. Some examples as to how you can set up the register values are also in your notes. Again, I'll let you peruse those. This is how we turn it into something in practice. So this is an example of a 50 millisecond delay implemented in hardware. So we're configuring the timer. We have no interrupts in this case. We load the timer values using the calculations on the previous slide. And now we wait for the timer to overflow. This code is not completely independent of the compiler settings, but it's much more independent of the compiler settings than the delay code we looked at previously. So it gives us a good way of creating well-defined hardware delays. We can put this into a loop and create longer delays with this. On the 8051, with a 12 megahertz oscillator in a standard 8051 configuration, the longest delay you can create through this route is 65 milliseconds. So if you want longer delays, you need to set up a loop to do these, which is not perfect, but you can achieve that result. We can do something more useful. So there's code for reading from an analog to digital converter. Here's code from reading from a switch pin. Both unbounded, because we don't know whether the switch is going to be connected correctly. We don't know whether the user is going to release the switch. We don't know whether the analog to digital converter has been set up correctly and whether it will ever complete its calculation. We can create a timeout loop in our code. So in this case, well, how does this work?
Testing for both conditions being true.
Okay, so what happens in practice then? Suppose that can
Timeout value not be something of the type, a fixed value rather than not zero.
doesn't matter in terms of the concept. It could be any value you like. So you could set it to a lower value to have a quicker timeout, and that would be fine. What would actually happen here then?
If it reaches timeout loop, if it reaches the
So every time it goes round that loop, so every time it's gone round here, it just keeps incrementing timeout loop because it started at 0, incrementing it until it wraps round back to 0. And then if this condition has not changed to 1 before this wraps round to 0, then the loop will terminate. So at least we know that the loop will eventually terminate. We don't know how long that will take without knowing about the oscillator frequency and everything else. So it's not brilliant, but it's better. because at least we know now that the loop will eventually terminate. We can do a much better job. So there's an example in there that shows you the thing running. Here's a much better job. We're configuring our hardware. So we set up one of the timers in our hardware as a 16-bit timer, disable interrupts, and set the timer to overflow after 10 milliseconds. And when it overflows, TF0 will be set to 1. So we clear the flag, start the timer, start reading, in this case, our analog to digital converter. And if after, in this case, 10 milliseconds, the A to D conversion hasn't completed, we will still leave this loop. So now we have a worst case execution time for this block of code, which is known and which is approximately 10 milliseconds. And that's a step improvement. In reality, we wouldn't need that long a time. Most analog to digital conversion operations by now take a few microseconds, so this might be set to 1 millisecond or something, and it would time out quite quickly, and it would give us a much more reasonable worst case execution time, but the concept would remain exactly the same. So we've now got a hardware loop timeout built into this system. If we wanted to do so, we can take this concept one step further. Suppose we set a timer to overflow after 5 milliseconds, call a function, and then wait for the timer to overflow. So we do that function. Assuming that that's about 4 milliseconds in duration, but it might have a variable execution time. So we set this to a 5 milliseconds overflow period. We run X. We then wait until 5 milliseconds have elapsed, and then we run Y. No interrupts, but we've ensured that that function starts 5 milliseconds after that function, regardless of any variations in the execution time of the first function. And that might be useful if we need to guarantee the timings of these systems. We'll look at other ways of dealing with this tomorrow when we're using our interrupts and a scheduler, but that's one way of achieving this result. So in this case, this is the simplest way of creating running X, having a delay, running Y, and creating a delay. We'd have very little control over the timing here if X and Y have a variable duration, the variable execution time. If we run it like this, with each one running in a sandwich delay, we get a bit more control over the time. One final example. So what does this do?
Runs X, but then it's got a delay. I don't know, you might have put something in there, but you don't know what the delay is, I guess.
Okay.
It runs Y, then you tell it to power down. But then you've got your safety after the power down.
Sometimes called a one-shot system. Runs X, we have a delay, which may be fixed, may not be perfectly fixed, and we run Y. Then the system basically powers down. In most systems, if it really has powered down, the only way to make it start again is to actually reset the power. do a power on reset. Now remove the power, re-engage the power again. This system, what do I do to make it run X? This is going to be a system that looks pretty much like this, probably. It's going to have one button on it. We press that button, and it will then, we'll run X, we'll run Y, and then that's it. We press the button, we'll run X, we'll run Y. What does the button press do? What happens when I press the button? Is there switch? Well, there is no switch reset reading code in here. Yeah. So it's a reset. So what this button press is doing is it's resetting the system. It's a power on reset for the system, and the system is always on. Always on, but it's in power down mode. And in most cases, the power consumption in power down mode, is so low. Perhaps it's not working. Power consumption in power down mode is so low that it doesn't make any difference whether you're in power down mode or whether the batteries are sitting on the shelf, gradually decaying. It makes virtually no difference. You'll still get a year of life out of the batteries if they're sitting most of the time in power down mode. So it goes into power down mode, sits there until someone presses the reset button again, and we get this kind of behavior. If you have electric garage doors, you're probably running something like this. Your car alarm, car access system, etc., is probably running something similar, and so on. Very simple architecture, but one which is sometimes useful. Right, that's where we're going to stop for now, and we'll then let you have an exercise to work on for this afternoon.